In the race to develop safer and more durable batteries, low self-discharge capability is a key factor. Water-in-Polymer Salt Electrolyte has emerged as a promising solution for organic batteries. By retaining up to 99% of energy each month, Whipsy prevents battery drain even during long periods of inactivity. So what gives it this outstanding advantage? Before we begin, please help us reach 8,700 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Model Q, Tesla EVs, and the latest news. How does the Water-in-Polymer Salt Electrolyte enable slow self-discharge in organic batteries? The biggest barrier preventing organic batteries from being widely applied is the rapid self-discharge phenomenon, meaning the quick voltage drop while the battery is not in use. In organic batteries using traditional aqueous electrolytes, free water tends to diffuse and react with electrode materials, leading to charge loss and damage to molecular structures. Recent studies have shown that organic batteries with aqueous electrolytes lose up to 30 to 40% of their voltage after just a few hours when left at open circuit. This makes devices using such batteries unstable, unable to store charge for long periods, and very difficult to commercialize. This is also why most previous studies, despite achieving good capacity, either do not publish or deliberately ignore the self-discharge rate, a serious but rarely mentioned problem. However, a breakthrough came with the invention of a new electrolyte called Water-in-Polymer Salt Electrolyte, developed by a research team at Chalmers University of Technology, Sweden. The uniqueness of Whipsy lies in its chemical mechanism and material structure. Instead of allowing free water to exist in the electrolyte solution, the researchers used a supramolecular polymer network to trap water molecules in hydration cages. There, salt ions at very high concentrations, the molar ratio of salt to water far exceeds that of conventional solutions, are organized within a porous polymer structure, minimizing free water diffusion and thereby significantly reducing charge leakage currents. This mechanism not only limits water contact with the electrode surface, but also maintains the necessary ion transport for the charge-discharge process. Water in Whipsy still acts as an ion-conducting medium, allowing ion flow from the cathode to the anode, but it is anchored by the polymer network and sulfonate ions, preventing free contact or side reactions with the electrodes. This is considered a unique water confinement system that stabilizes the chemical and electrochemical properties of organic batteries. Experiments show that batteries using Whipsy maintain voltage for 7 continuous days without recharging, while batteries with traditional aqueous electrolytes lose almost all their voltage after just 10 hours. The self-discharge reduction exceeds 80%, opening unprecedented potential for long-term storage in organic batteries. Physically and chemically, the polymer network in Whipsy creates a stable environment for sulfonate salt ions with a high ion density, comparable to an ion supersaturation state, boosting ionic conductivity to about 1 millisiemens per centimeter. This porous and tightly bonded structure also prevents free water diffusion, minimizing electrode decomposition reactions that cause energy loss. At the same time, Whipsy maintains a wide electrochemical voltage window of about 1.8 volts, significantly higher than conventional aqueous electrolytes, which only reach about 1.0 to 1.2 volts, providing stable performance and safe operation. Additionally, the confinement of water within the polymer network greatly reduces evaporation and temperature fluctuations inside the battery, helping maintain electrolyte structural stability under real operating conditions ranging from 20 to 70 degrees Celsius. This significantly improves the battery's lifespan and performance in automotive or mobile devices that require long-term stability. Another advantage of WiPSE is its design flexibility. This electrolyte can be formed into gels or thin films, enabling applications in thin, flexible, or directly printed organic batteries using electrodes such as polythiophene, polyanthraquinone, or lignin. Tests combining Whipsy with these organic electrodes show capacity retention over 1,000 cycles without significant degradation, compared to batteries using traditional aqueous electrolytes, which only retain about 200 cycles before capacity drops by more than half. Finally, Whipsy not only delivers outstanding performance, but is also environmentally friendly and easy to manufacture at low cost. Its main components such as sulfonate salts, polyethylene glycol, and hydrocarbon-based polymers can be synthesized at low temperatures without toxic solvents and are biodegradable after their life cycle. This helps reduce environmental pollution compared to current organic electrolytes and opens a sustainable development path for organic batteries in the future. Once again, please help us reach 8,700 subscribers. This is important for us to stay motivated. Thank you. How does Whipsy contribute to making EV batteries lighter, more compact, and high-performing? The battery is the heart of every electric vehicle, and it is also the heaviest part of the car. For a popular model like the Tesla Model Y, the battery pack can account for nearly 1/4 of the vehicle's total weight, approximately 480 to 500 kilograms. This weight affects both the vehicle's performance and increases production costs and energy consumption. Therefore, engineers and researchers continuously seek to optimize battery design to reduce weight, enhance efficiency, and simultaneously ensure safety. Among the most outstanding emerging technologies, Water-in-Polymer Salt Electrolyte, or WiPSE, is receiving special attention. Instead of using the liquid organic electrolytes typical of traditional lithium-ion batteries, which are quite heavy, flammable, and carry the risk of fire or explosion, WiPSE uses an electrolyte mainly composed of water tightly held within a polymer network. This brings two major benefits: significantly reduced weight and markedly improved safety. Water is non-flammable and also helps eliminate the toxic solvents commonly found in current batteries. A notable point is that WiPSE can reduce the battery pack weight by 50 to 70 kilograms compared to conventional lithium-ion batteries. While this number may seem small relative to a 2-ton vehicle, every kilogram reduced helps improve operational efficiency, decrease suspension wear, enhance acceleration, and lower energy consumption. This is particularly important for models like the Tesla Model Y, which users expect to have long driving ranges and smooth driving experiences. Not only lighter, WiPSE also allows the battery components to be designed closer together. In this case, lithium ions have a shorter distance to travel during charging and discharging, reducing resistance and increasing electrical conductivity efficiency. As a result, the battery's energy density increases significantly, potentially reaching 350 to 400 watt-hours per kilogram, 15 to 20% higher than traditional batteries. Therefore, electric vehicles using WiPSE batteries can travel longer distances without increasing the size or weight of the battery pack. Regarding charging speed, WiPSE enables batteries to withstand fast charging up to 3C, meaning a full charge can be completed in about 20 minutes, much faster than traditional lithium-ion batteries that currently handle only about 1 to 1.5 C. This is a significant improvement, saving users time and increasing convenience for electric vehicles on long trips or when quick recharging is needed. Safety is an indispensable factor. WiPSE, with its primarily water-based composition, reduces the risk of fire or explosion when the battery is impacted or malfunctions. This not only protects users, but also allows for thinner protective layers around the battery, further reducing weight and cost. At the same time, WiPSE is less prone to electrolyte leakage, which is a common cause of damage or short circuits in current battery types. Of course, WiPSE still faces several challenges. One of them is how to maintain a stable amount of water in the polymer during high-temperature operation to avoid evaporation that would reduce performance. Research teams are developing new polymers with better water retention and enhanced mechanical strength. Additionally, the vehicle's thermal management system plays a critical role in maintaining stable operating temperatures for WiPSE batteries. The electrochemical compatibility between WiPSE and electrode materials is also emphasized. Without optimization, side reactions may occur, affecting battery lifespan and performance. However, according to multiple research reports, WiPSE batteries can retain over 80% capacity after more than 1,500 charge-discharge cycles, outperforming many lithium-ion batteries currently on the market. Moreover, WiPSE technology contributes to reducing environmental impact throughout the battery's production and disposal cycle. Limiting the use of toxic organic solvents is not only safer for workers, but also reduces pollution risks when batteries are discarded. This is an important step toward the sustainable development goals of the electric vehicle industry. For Tesla, applying WiPSE not only improves the performance of the Model Y, but also strengthens its pioneering position in electric vehicle battery technology. Tesla is already famous for many innovations such as the cell-to-pack design to increase battery density, or the GigaPress, a large casting machine that reduces parts and vehicle weight. Whipsy will be a perfect addition for Tesla to continue lowering battery weight, enhancing safety, and expanding vehicle design possibilities. Whipsy offers many great benefits: weight reduction, increased energy density, improved design flexibility, enhanced safety and battery lifespan, and greater environmental friendliness. Although technical challenges remain ahead, it is clearly one of the promising technologies that could usher in a new era for electric vehicle batteries. Then, models like the Tesla Model Y will become lighter, drive farther, charge faster, and be safer, making the transition to electric vehicles not only a trend, but also a great sustainable experience for users. How does low self-discharge impact battery safety? The Water-in-Polymer Salt Electrolyte is considered a significant advancement in enhancing the safety of organic batteries, especially for electric vehicle applications. Traditional lithium-ion batteries use liquid organic electrolytes, which are flammable and have a flash point around 120 degrees Celsius, posing a high risk of fire and explosion in the event of a malfunction. Statistics show that over 100 electric vehicle battery fires have been recorded in just the past 5 years, with most incidents linked to liquid electrolytes. In contrast, Whipsy mainly consists of water, which has a flash point above 100 degrees Celsius and is inherently non-flammable. Whipsy also reduces self-discharge to below 1% per month, much lower than traditional lithium-ion batteries, which can experience 3 to 5% monthly self-discharge. This improvement not only extends battery lifespan to over 2,000 charge-discharge cycles, double that of many current batteries, but also lowers the risk of heat generation and explosion during long-term storage. Additionally, the Whipsy electrolyte avoids the common leakage issues found in traditional batteries, which often cause short circuits and damage. Upon decomposition, Whipsy does not emit toxic gases like hydrofluoric acid or flammable gases such as ethylene, thus minimizing hazards to users and the environment. Compared to solid electrolytes, Whipsy enables ion transport that is 5 times faster due to water's facilitation within the structure. Manufacturing costs for Whipsy are also estimated to be 20 to 30% lower than those for solid electrolytes, owing to simpler production processes and more readily available materials. However, the boiling point of water in Whipsy is about 100 degrees Celsius, which can lead to evaporation when the battery operates at high temperatures above 60 to 70 degrees Celsius during fast charging or continuous use. These temperatures are common in many electric vehicles today, so developing polymers that better retain water and implementing specialized cooling systems are essential. Laboratory tests have shown that new polymers can retain up to 95% of their water content after 1,000 hours at 80 degrees Celsius, helping to prolong battery life and stabilize performance. Compatibility between Whipsy and electrode materials is also carefully studied to minimize side reactions, maintaining over 90% efficiency after 1,000 charge-discharge cycles. Electric vehicle batteries typically operate across a temperature range from -20 degrees Celsius to 60 degrees Celsius, enduring vibrations and shocks during use. Traditional batteries usually degrade below 70% capacity after 1,000 to 1,500 cycles, reducing driving range and safety. Whipsy's water retention and stable polymer structure help limit capacity fade, maintaining over 80% capacity after 2,000 cycles, equivalent to more than 8 years of typical electric vehicle usage. Its very low self-discharge rate, under 1% monthly, reduces energy loss during periods of inactivity, extending storage time and lowering maintenance costs. Still, temperature management remains a major challenge. Modern fast charging can heat batteries above 70 degrees Celsius, causing water evaporation and electrolyte degradation. Effective cooling systems that maintain temperatures below 40 degrees Celsius can extend battery life by 25 to 30% compared to uncontrolled operation. Research also shows that the electrochemical compatibility of Whipsy with lithium electrodes can achieve over 99% ion storage efficiency, minimizing side reactions and preserving electrode structure stability over many cycles. Therefore, Whipsy not only represents a major leap forward in safety, but also promises significantly longer battery lifespan under harsh operating conditions. Successful advances in polymer development, thermal management, and electrode optimization will enable future electric vehicles to become safer, more durable, and more cost-effective. We appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno Creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.